Space is far stranger than any science fiction story. The cosmos hides realities that defy our basic understanding of existence. And today, we will explore 25 phenomena that prove it. You will leave this journey with a completely new perspective on the universe. We will venture into a void so vast it redefines emptiness and confront objects where the laws of physics break down entirely. How much of the universe do you think remains hidden from our view, stretching across a region of space nearly 330 million light-years wide, is a chilling emptiness known as the Boötes Void? Think of our familiar universe with its brilliant galaxies scattered like cities across a dark landscape. Now, imagine a hole in that landscape so colossal that you could fly for hundreds of millions of years and see almost nothing but an unbroken, profound blackness. This is the Great Nothing. When astronomers first stumbled upon it, they could scarcely believe the data. In a typical volume of space that size, you would expect to find at least 10,000 galaxies. Here, they have found only a few dozen. It is a cosmic desert on a scale that is almost impossible for the human mind to grasp. Its very existence defies our simplest models of the universe, which predict matter should be spread more or less evenly, like raisins in a rising loaf of bread. Instead, the cosmos reveals itself to be lumpy and full of holes, a vast cosmic web where immense filaments of dark matter and galaxies are separated by these staggering voids. The Boötes Void is not just an empty room, it is a missing continent in the fabric of reality. How does such a void even come to be? One theory suggests it is the result of smaller voids merging over billions of years, like soap bubbles coalescing into one giant bubble. Its presence forces us to confront profound questions about the initial conditions of the Big Bang and the mysterious, repulsive force of dark energy that may be stretching these voids ever larger. So if the Boötes Void represents a terrifying absence, our next phenomenon is its polar opposite, a point of such extreme density that not even light can resist its pull. Gravity itself becomes a prison at the edge of a black hole. This boundary, known as the event horizon, is the ultimate point of no return. Cross it, and every possible path leads inward toward the crushing heart of the black hole, a point of infinite density called a singularity. Here, the cosmos as we know it ceases to be. The laws of physics, which have guided our understanding from the orbit of planets to the glow of distant stars, simply break down. Matter is compressed into a realm where space and time are no longer separate concepts, but are twisted into something beyond our comprehension. These objects are not the destructive monsters of fiction, but rather cosmic laboratories, testing the very foundations of reality. We have now seen their shadow, a dark silhouette encircled by a fiery ring of superheated gas, captured by the global network of telescopes known as the Event Horizon Telescope. This image confirmed their existence in a way theory alone never could. The effects are as bizarre as they are extreme. An astronaut falling toward a black hole would experience spaghettification, stretched into a long, thin strand by the intense gravitational gradient. From our distant perspective, we would see their clock slow to a crawl, a phenomenon called time dilation, until they appeared to freeze at the event horizon, their image fading over eons. But perhaps the most mind-bending discovery came from Stephen Hawking, who proposed that black holes are not entirely black. Through quantum effects at their very edge, they can slowly leak radiation, evaporating over timescales so vast they dwarf the current age of the universe. This revelation leads to one of the greatest paradoxes in physics. What happens to the information that defines the identity of every particle that falls in? Is it lost forever, violating a fundamental law of quantum mechanics, or is it encoded in the Hawking radiation? We simply do not know. These gravitational behemoths are gateways to the unknown, challenging our most basic assumptions about information, causality, and the fabric of spacetime. But to see the most distant and hidden parts of the universe, we rely on a cosmic trick of light, a natural illusion that acts as the universe's own telescope. That same gravity which forges black holes also creates the universe's most powerful telescopes. When a massive object like a galaxy cluster sits between us and a more distant light source, its immense weight warps the very fabric of spacetime around it. Light from the background object traveling through this distorted space does not follow a straight line. Instead, it bends, curving around the foreground mass like a car following a banked racetrack. The result is a cosmic illusion, a trick of gravity called gravitational lensing. We might see multiple smeared or magnified images of a single, faraway galaxy. In the most perfect alignments, the warped light forms a complete circle known as an Einstein ring, a shimmering halo in the depths of space. This is not just a beautiful confirmation of Einstein's theory of general relativity. It is a tool. Gravitational lensing acts as nature's own telescope, amplifying the faint light from objects so distant they would otherwise be invisible to our most powerful instruments. It allows us to peer back at the earliest galaxies, infant structures forming just after the Big Bang, but its true power lies in revealing the invisible. The amount of bending we observe tells scientists how much mass is present in the foreground cluster. Often, the visible galaxies alone do not account for the severe warping of light. The lens is being shaped by the immense, unseen halo of dark matter enveloping the cluster. By meticulously mapping these distorted images, astronomers can literally chart the distribution of this mysterious, invisible substance that makes up most of the universe's mass. They can even use it to probe the properties of dark energy, the force accelerating cosmic expansion, by observing how lensing effects change over vast cosmic timescales. The cosmos uses its own gravity as a funhouse mirror, distorting reality to show us what is truly there. Yet for all the clarity lensing can provide, some cosmic signals remain stubbornly chaotic and impossible to predict. While gravitational lensing reveals the universe's large-scale architecture, some of the cosmos's most compelling mysteries are written in the flickering light of a single, unassuming star. KIC 8462852, better known as Tabby's star, behaves like no other. Its light doesn't dip in the regular, predictable rhythm of an orbiting planet. Instead, it flickers and fades in chaotic, dramatic plunges, sometimes dimming by an astounding 22% before slowly returning to normal. This is not a slight shadow. It is as if a colossal, jagged shape is periodically drifting in front of the star, blocking a massive portion of its light. When citizen scientists from the Planet Hunters project first spotted this bizarre pattern in data from the Kepler Space Telescope, the astronomy community was stunned. Nothing in our conventional understanding of stellar systems could easily account for it. A planet, even a gas giant, would block at most 1% of a star's light. This was something else entirely, something on a staggering scale. The most tantalizing, though least probable, hypothesis was that we were witnessing the construction of an alien megastructure. Imagine a civilization so advanced that it builds a vast network of collectors, a partial Dyson sphere, around its host star to capture nearly all of its energy output. Such a structure would not be solid and uniform, but a swarm of orbiting platforms that could create the irregular, deep dimming patterns we observe. It was a concept ripped from science fiction, yet for a brief moment it seemed like a remote possibility. Of course, scientists prioritized natural explanations. Perhaps a huge, fragmented family of comets was swarming the star, or a massive cloud of interstellar dust was passing through the system. Years of intense follow-up observations have since ruled out some of the simpler ideas. The star's long-term, subtle dimming over a century of archival data only deepened the puzzle. The current consensus leans toward a natural, if extraordinary, cause, likely involving uneven clouds of fine dust orbiting the star. This dust could be the debris from a catastrophically shattered planet or moon, creating a complex and evolving cloud of fragments, but the definitive answer remains elusive. Tabby's star stands as a powerful reminder that our catalogue of cosmic phenomena is far from complete. It challenges us to question our assumptions and holds open the door, however slightly, to the profound possibility that we might one day see the fingerprint of another intelligence written in the stars. This cosmic puzzle operates on an immense scale, but to understand the true fabric of reality, we must shrink our perspective to the realm of the vanishingly small. Two particles born from the same event can become forever linked, their fates intertwined in a way that defies all common sense. Separate them by the width of a lab bench or the distance between continents, and they remain a single, unified quantum system. Measure a property of one, like its spin, and its distant partner instantly assumes a corresponding state. This is quantum entanglement, a phenomenon so strange that Albert Einstein dismissed it as spooky action at a distance. He was deeply troubled by the implication that information seemed to be traveling faster than light, violating the cosmic speed limit set by his own theory of relativity. Yet decades of meticulous experiments have proven entanglement is real. It is not a flaw in our theories, but a fundamental feature of our universe. This bizarre connection operates outside the realm of classical physics we experience every day. In our macroscopic world, objects are separate and influences travel at a finite speed. In the quantum realm, this separateness is an illusion. The particles do not send a signal to one another. Instead, they behave as parts of a single whole, regardless of the space between them. This challenges our most basic ideas about locality, the concept that objects are only influenced by their immediate surroundings. The practical applications of this spookiness are profound. Quantum computers leverage entangled bits or qubits to perform calculations that would take conventional supercomputers millions of years. Quantum cryptography uses the principle to create theoretically unbreakable codes because any attempt to eavesdrop on an entangled message instantly disturbs the connection and alerts the users. Scientists have successfully entangled particles over distances of more than 1,000 kilometers, beaming the linked states between ground stations and satellites. Some physicists even speculate that the very fabric of spacetime, the stage upon which the universe plays out, may be woven from a vast cosmic web of entangled connections. How can reality be so deeply interconnected? The answer remains one of the greatest mysteries in physics, pointing to a cosmos where separation itself may be the ultimate illusion. Yet while entanglement connects particles across silent voids, the cosmos also produces bursts of energy so violent they can be seen from billions of light years away. From the bizarre connections of the quantum world, we are thrown back into the vastness of space by a sudden, deafening scream. A flash of radio waves from the edge of the observable universe can release more energy in a single millisecond than our sun emits over 80 long years. These are fast radio bursts, or FRBs, cosmic enigmas that appear without warning and vanish just as quickly. Discovered by accident in 2007 when astronomers were sifting through old data, these events are so brief that for years many wondered if they were glitches. But the signals were real, and they were coming from billions of light years away. The mystery only deepened when we found that some of these bursts are loners, a single, brilliant shout into the dark. Others, however, repeat. They sputter back to life from the same patch of sky, firing off signals in a sporadic, unpredictable cadence that defies any simple explanation. What kind of cosmic engine can switch on and off so violently and so fast? The leading suspects are the most magnetic objects in the universe, magnetars. These are a type of neutron star, the collapsed core of a giant star, with a magnetic field so powerful it could strip the information from every credit card on Earth from a distance halfway to the Moon. In 2020, a magnetar within our own galaxy erupted with a radio burst that matched the signature of an FRB, finally giving us a confirmed source in our cosmic backyard. Yet the diversity of these bursts suggests magnetars are not the whole story. Could they also be produced by the cataclysmic collapse of a black hole, or the violent merger of two incredibly dense stars? The most speculative idea, though highly improbable, is that we are seeing the fallout from immensely powerful alien technologies, perhaps energy beams used to propel light sails across interstellar space. Beyond their mysterious origins, these bursts are useful tools. As they race across the universe, their waves are stretched and delayed by the tenuous clouds of electrons that drift in the space between galaxies. By measuring this distortion, astronomers can use FRBs as probes to weigh the invisible, missing matter that makes up the cosmic web. Each burst is a fleeting, brilliant message, carrying with it the signature of all it has passed through. We are left to wonder what cosmic events can be so powerful yet so brief, and why some celestial objects choose to whisper their secrets more than once. But the very fabric these signals travel through is shaped by a substance we cannot see, a ghost that holds the universe together. This ghostly presence holds our very galaxy together. All the stars, planets, and brilliant nebulae we can see are merely floating in a vast, invisible sea of dark matter. It is the cosmic architect, an enigmatic substance that does not interact with light in any way. It neither emits, absorbs, nor reflects it, rendering it completely transparent to our telescopes. Yet its gravitational influence is undeniable and overwhelming. We can see its handiwork in the way galaxies spin. According to the laws of gravity, stars on the outer edges of a spiral galaxy should orbit much more slowly than those near the bright core, just as Pluto takes far longer to orbit the Sun than Mercury does. But when astronomers measured these galactic rotations, they found something shocking. The outer stars race around at nearly the same speed as the inner ones. The only plausible explanation is that the entire visible galaxy is embedded within a colossal, massive halo of something we cannot see, a dark matter sphere whose immense gravity whips the outer stars along. This invisible scaffold is not a minor component. It is the universe's primary building material. For every ounce of ordinary matter that makes up you, me, and every star, there is 5 times more dark matter holding it all in place. Without this hidden anchor, galaxies would simply fly apart, their stars scattered into the intergalactic void. The hunt to identify what it is made of has become one of the greatest scientific quests of our time. The leading candidates have names that sound like science fiction. Weakly interacting massive particles, or WIMP, are hypothetical heavy particles that barely interact with normal matter. Then there are actions, theoretical ultralight particles that could be streaming through you by the billions every second. To catch one, scientists have built exquisitely sensitive detectors in deep underground laboratories, shielded from cosmic rays by a mile of solid rock. They wait for the impossibly rare moment when a dark matter particle might bump into the nucleus of an ordinary atom, So far, the detectors have remained silent. Particle colliders like the Large Hadron Collider are trying a different approach, smashing protons together at nearly the speed of light in the hope of creating dark matter particles from the immense energy of the collision. We would not see the particles themselves, but could infer their existence by an apparent imbalance in the energy and momentum after the crash. The profound implication is that most of the universe is made of something we do not understand. We are living in a cosmic house whose walls and framework are built from a material we have never touched or seen, a silent partner in the dance of the cosmos. But if dark matter is the gravitational glue holding the universe together, what is the mysterious force that is actively tearing it apart? The same force that builds galaxies is being overpowered by a deeper, more dominant presence. Dark energy is the universe's silent accelerator, a mysterious form of energy woven into the fabric of empty space itself. For much of the 20th century, cosmologists believed the expansion of the universe, born from the Big Bang, was gradually slowing down. The collective gravity of all the galaxies, stars, and dark matter was thought to be pulling on the cosmic fabric, applying a gentle brake to the initial explosion. Then, in the late 1990s, two independent teams made a shocking discovery. By observing a special type of exploding star, a supernova, in extremely distant galaxies, they could measure the expansion rate of the universe billions of years ago. They expected to see that the ancient universe was expanding faster than today's, showing the clear deceleration. Instead, the data revealed the opposite. The expansion is speeding up. It is as if you tossed a ball into the air, and instead of falling back down, it shot away from you faster and faster, defying gravity itself. This cosmic acceleration is driven by dark energy, a repulsive force that acts like an anti-gravity on the largest scales. Its influence is so profound that it now constitutes about 68% of the entire energy density of the cosmos, making it the dominant component of the universe. We are living in the age of dark energy. The nature of this force is a profound puzzle. The simplest explanation is that it is an intrinsic property of space itself, what Albert Einstein once called the cosmological constant. In this view, even a perfect vacuum possesses a fundamental energy that pushes space apart. The problem is that when physicists try to calculate the strength of this energy using quantum mechanics, they get a number that is 120 orders of magnitude too large, a value so colossal it would have torn the universe apart in an instant. This is arguably the worst theoretical prediction in the history of science. The alternative is that dark energy is not a constant, but a dynamic field that changes over time, a sort of cosmic cousin to the field that drove the universe's explosive inflation in the first moments after the Big Bang. This idea opens up dramatic possibilities for the ultimate fate of everything. Will the acceleration continue at a steady rate, leading to a big freeze where the universe expands into a cold, dark, and lonely void? Or could the repulsive force grow stronger, ultimately overwhelming the nuclear forces inside atoms and shredding every star, planet, and molecule in a catastrophic big rip? The answer hinges on the true identity of this mysterious energy. We are left with a universe whose primary ingredient is a complete enigma, a force we cannot control or contain, silently guiding the destiny of all we see. Yet for all its dominance, dark energy cannot erase the violent echoes of the universe's birth, imprints left on the oldest light in existence. A star that refuses to die paints a terrifying new picture of stellar death. These are the zombie stars, cosmic survivors that endure their own supernova explosions and stagger onward, shining from the ashes of their catastrophic demise. The typical life cycle of a star is a story with a clear ending, either a quiet fade into a white dwarf or a violent collapse into a neutron star or black hole. A supernova was thought to be the final, definitive blast, the star's core obliterating itself completely. But then we found Type IX supernova. These are the stellar equivalent of a bomb that only partially detonates. They occur in a binary system where a white dwarf, the dense corpse of a sun-like star, siphons material from its companion. It reaches the critical mass needed for a thermonuclear explosion, but instead of a complete self-annihilation, the blast rips through the star in a more uneven, weaker way. The white dwarf is not destroyed. It is brutally wounded, hurling a portion of its material into space while the damaged remnant is left behind, reigniting and continuing its strange second life. How is this even possible? The physics is still being untangled, but it suggests the nuclear flame may not propagate evenly through the star. Some parts might burn while others are simply blasted away, leaving a scarred but active stellar core behind. Observations from the Hubble Space Telescope have identified several brilliant candidates for these zombie stars, white dwarfs that appear to be shining with the intense heat of their own incomplete destruction. This forces us to rewrite the textbook on how stars die. Stellar death is not always a single, final event. It can be a process, with some stars experiencing multiple violent outbursts over their long lives. The existence of these cosmic survivors adds a profound layer of complexity to our stellar models, revealing that the final moments of a star can be as varied and unpredictable as life itself. If a star can cheat death, then perhaps it is not so surprising that we have also found a planet that defies all logic by existing where it should not. Gas giants were never supposed to exist this close to fire. A planet like Jupiter, but orbiting so near its star that a full year passes in just a few Earth days, is a hellscape defying all early expectations. This is a hot Jupiter, a world where temperatures soar to thousands of degrees, hot enough to vaporize iron and tear apart molecules. When the first of these infernal giants was discovered in the 1990s, it sent a shockwave through astronomy. Our theories of planet formation were built on the calm, orderly blueprint of our own solar system, where giant planets form slowly in the cold, outer regions where ice is plentiful. A gas giant next to its star made as much sense as a snowball in a furnace. Their existence forced a dramatic rewrite of the rules. We now understand these planets are cosmic travelers. They likely form in the cooler outskirts of their systems, but gravitational tugs from the planet-forming disk or chaotic encounters with sibling planets can send them spiraling violently inward. This planetary migration is a destructive dance, often kicking smaller, Earth-like worlds out of the system entirely or sending them careening into the star. Once a hot Jupiter is parked in its scorching close orbit, the stellar radiation is relentless. The outer layers of its atmosphere are boiled away, streaming into space in a vast, glowing tail that makes the planet resemble a giant comet. This very destruction, however, gives us a window into its nature. As the planet transits or passes in front of its star, starlight filters through its evaporating atmosphere. By analyzing that filtered light, astronomers can perform a technique called transmission spectroscopy, identifying the chemical fingerprints of substances like sodium, water vapor, and even titanium oxide in the skies of these distant worlds. They are laboratories for studying extreme atmospheric physics. How can any atmosphere withstand such an onslaught? The answer lies in a constant, desperate balance between the star's fury and the planet's own powerful gravity, which struggles to hold onto its gaseous envelope. These monstrous worlds are a stark lesson in cosmic chaos, proving that our peaceful solar system is just one possible outcome in a galaxy full of violent, unpredictable histories. From the frantic orbits of these burning giants, we turn to an object spinning so fast it stretches the very fabric of space. The magnetic fury of a magnetar defies all earthly experience. This stellar powerhouse begins its life in the most violent of deaths, as the collapsing core of a massive star compresses into a city-sized sphere of ultra-dense neutron star material. But a magnetar is no ordinary remnant. Its interior is a churning, superconducting fluid of neutrons, and in the first chaotic seconds after its birth, this fluid can generate a magnetic field of almost unimaginable intensity. We are not talking about the kind of force that can move a compass needle. This field is a quadrillion times stronger than Earth's protective magnetic shield. At such extremes, the magnetic field ceases to be an invisible force and becomes a tangible, destructive entity. It can literally rip atoms apart, deforming them into long, thin cylinders in a process called magnetic stripping. The field exerts such immense stress on the star's own solid iron crust that it can crack it, triggering catastrophic starquakes. These quakes release immense vibrations through the star, snapping magnetic field lines and reconnecting them in colossal explosions of energy. The result is a giant flare. In a mere tenth of a second, a single magnetar flare can unleash more energy than our sun will radiate over 100,000 years. For that brief instant, the magnetar outshines every star in its host galaxy. If such a flare were to occur within a few thousand light-years of Earth, the consequences would be severe. The blast of radiation, while not immediately lethal to life on the surface, would likely ravage our planet's protective ozone layer, leaving us exposed to the sun's harsh ultraviolet light for years. These objects are not just theoretical monsters. We have observed their outbursts, events known as soft gamma repeaters, which send waves of less energetic gamma rays washing over our detectors at unpredictable intervals. Each flash is a direct signal from a celestial body under almost unbearable internal strain, a testament to the raw, untamed power that the universe can wield. The very existence of magnetars forces us to question the limits of matter and energy, revealing a cosmos where forces we consider fundamental can be amplified into something truly terrifying. This exploration of a broken symmetry reveals a universe that seems to have chosen matter over antimatter from the very beginning. Something in the first moments of creation broke the symmetry. The universe began as a perfect, seething furnace of matter and its mirror opposite, antimatter. For every particle of matter born, an antiparticle should have emerged, its identical twin in every way except for an opposite electric charge. When these twins meet, they annihilate each other in a flash of pure energy, leaving nothing behind. Given this perfect balance, the entire cosmic story should have ended almost as soon as it began, with every last particle cancelling out its antiparticle, leaving a universe filled with nothing but a fading sea of radiation. Yet here we are in a cosmos filled with galaxies, stars, planets, and life, all made of matter. This is the great cosmic imbalance, the matter-antimatter asymmetry, and it stands as one of the most profound puzzles in all of science. Why was there one extra particle of matter for every billion particle-antiparticle pairs? That 1 in a billion surplus is all that remains, the entire visible universe built from that tiny, inexplicable excess. To account for this, physicists know that the laws of physics must contain a built-in preference for matter, a subtle bias that allowed it to win the ultimate cosmic war. This required a violation of a principle known as CP symmetry, a concept that combines charge conjugation, which switches particles with antiparticles, and parity, which mirrors spatial coordinates. In essence, CP symmetry states that the laws of physics should treat matter and antimatter identically, but we have observed tiny, precise experiments where this symmetry breaks. In the decay of certain exotic particles called kaons and B mesons, matter behaves very slightly differently from antimatter. The problem is that the level of CP violation we have measured is far, far too small to explain the overwhelming dominance of matter we see in the cosmos. It is like finding a single bent coin in a pile of a billion perfectly fair ones when you need a whole mountain of bent coins to build a universe. This discrepancy points to something fundamental missing from our standard model of particle physics. Theorists are chasing answers in realms like leptogenesis, where the decay of incredibly heavy, hypothetical neutrinos in the early universe could have tipped the scales. Others look to grand unified theories or even the properties of the Higgs boson for clues. The answer lies in new physics, in forces or particles we have not yet discovered. The question is no longer just a technical one for physicists, it is deeply philosophical. Why is there something, anything at all, rather than an everlasting, featureless void of light? Our very existence hinges on a broken symmetry written into the first seconds of time. And just as this mystery challenges our understanding of cosmic origins, another compels us to question the very nature of cosmic structures, where an entire galaxy is dominated by the invisible. A ghost galaxy drifts through the void, its vast form built from everything needed for stellar fire, yet cloaked in an almost perfect darkness. These are dark galaxies, cosmic phantoms that challenge our very definition of what a galaxy can be. Picture a structure the size of the Milky Way, brimming with immense clouds of hydrogen gas and anchored by a massive halo of dark matter. Yet where we would expect to find hundreds of billions of brilliant suns, there are only a handful or perhaps none at all. This is not an empty void, but a place brimming with potential that has somehow remained unfulfilled. Theorists have long suggested such objects should be common, especially in the early universe. They could be the primordial building blocks, the cosmic bricks that merged through gravity to form the grand spiral and elliptical galaxies we see today. Finding them, however, is a monumental challenge. How do you see a galaxy that refuses to shine? The hunt relies on subtle tricks of observation. Radio telescopes scan the skies for the faint, characteristic glow of neutral hydrogen gas. When they find a large, rotating cloud of this gas with no visible stars to account for its motion, a candidate is born. These HI regions, isolated in the blackness, could be pristine dark galaxies, cosmic fossils preserved from a time before widespread star formation. The interpretation is not always simple, as similar clouds can be torn away from normal galaxies during violent gravitational encounters, leaving behind tidal debris that masquerades as an independent object. But the confirmed existence of even a few true dark galaxies would force a profound rewrite of astrophysics. They possess all the raw materials for star birth, the gas and the gravity to pull it together. So what cosmic switch remains flipped to the off position? Perhaps their dark matter halos are not dense enough to compress the gas effectively, or maybe the gas itself is too turbulent to collapse into stable cores. Supernova explosions from the first few stars could have blown the rest of the gas away, preventing further growth. These objects are living experiments, testing the delicate and poorly understood conditions required to ignite stellar fusion. They are the hidden population of the cosmos, a silent majority whose discovery could reveal the missing links in the story of how our brightest structures were assembled from the dark. If entire galaxies can hide in plain sight, could our entire universe be just one bubble in an infinite cosmic foam? Our universe may be just one island in an endless cosmic archipelago. The concept of the multiverse suggests that everything we can observe, from the most distant galaxy to the laws of physics themselves, is merely a local set of conditions within a far vaster and more varied reality. This isn't science fiction, but a serious, though speculative, extension of our best physical theories. The idea emerges naturally from cosmic inflation, the theory that our universe underwent a period of hyper-fast expansion in its first moments. If inflation is eternal, as some models suggest, then new pocket universes could be continuously bubbling into existence, each one a separate cosmos with its own random set of physical constants. String theory, a candidate for a theory of everything, proposes that the fundamental properties of our universe are determined by how tiny, vibrating strings of energy are curled up in extra-spatial dimensions. The mathematics suggests there could be a staggering number of possible stable configurations, perhaps 10 to the power of 500, each one representing a different universe with different laws. Even the strange rules of quantum mechanics contribute, with the many worlds interpretation proposing that every quantum decision branches reality into a new timeline, creating an ever-expanding tree of parallel worlds. In this grand tapestry of realities, some universes might have gravity so strong they collapse instantly back into nothingness. Others might have 5 spatial dimensions or a weaker nuclear force that prevents stars from ever igniting. Some could be composed of pure energy or dark matter with no atoms at all. This dizzying plurality offers a potential answer to one of the deepest mysteries, the fine-tuning problem. Why do the fundamental constants, like the strength of gravity or the mass of an electron, seem perfectly calibrated to allow for the existence of stars, planets, and life? If there are an infinite number of universes, then we simply find ourselves in one of the rare, habitable ones, a cosmic lottery winner. While this provides a compelling narrative, it is currently untestable, placing it at the frontier where physics meets philosophy. It forces us to ask what it means for our universe to be unique, and whether the nature of existence is fundamentally random. From contemplating an infinity of possible worlds, we are drawn back to our own by the steady, rhythmic beat of a star that should not be. The steady pulse of an RR Lyrae star is a cosmic clockwork, a stellar metronome ticking with unwavering reliability. These ancient suns, found in the dense globular clusters orbiting our galaxy's core, rhythmically breathe in and out, their atmospheres expanding and contracting over cycles lasting just hours. With each pulsation, their brightness rises and falls in a predictable, repeating pattern. This remarkable consistency makes them one of astronomy's most trusted tools, known as standard candles. Because the star's true, intrinsic brightness is tightly linked to the period of its pulse, astronomers can measure its apparent dimness from Earth and calculate its distance with stunning precision. They are the mile markers of the Milky Way, allowing us to map the vast, three-dimensional structure of our galactic neighborhood and even gauge distances to our closest galactic satellites. But sometimes the metronome stutters. Many RR Lyrae stars exhibit a secondary, more mysterious rhythm known as the Blaschko effect. Over weeks or months, the primary pulse begins to waver. The star's brightness at the peak of its pulse might grow stronger, then weaker, while the length of its cycle subtly shifts. It is as if a perfectly tuned instrument is being played by 2 different musicians at once, one keeping a steady beat and the other applying a slow, unpredictable pressure. The cause of this modulation remains one of the most stubborn puzzles in stellar astrophysics. It could be driven by complex magnetic fields churning within the star, or perhaps by a resonance between different pulsation modes deep in its interior, like 2 overlapping sound waves creating a beat. Another theory points to the star's own rotation, slowly twisting internal magnetic fields that then alter how the pulsations manifest at the surface. Each of these old, low-mass stars is a fossil from the early universe, and their pulsations allow scientists to perform stellar seismology. By studying the subtle changes in their light, we can peer into their hidden hearts, probing the structure and composition of matter under extreme conditions. The Blaschko effect, then, is not a flaw in the tool, but a complex message encoded in the starlight, a clue to the turbulent dynamics operating within these aging suns. Unlocking its secret would not only explain the erratic behavior of a trusted cosmic beacon, but also reveal new details about the internal lives of stars and the formation history of our galaxy itself. This stellar clockwork provides a map of our cosmic present, but to understand the universe's deepest past, we must find a relic from its very first moments. Our own solar system may be hiding a ghost, far beyond the orbit of Neptune, in the frigid darkness of the Kuiper belt. A handful of small, icy worlds are behaving strangely. Their orbits are clustered together, tilted at similar angles, and they swing out to their most distant points in a synchronized way that defies the gravitational pull of all the known planets. It is as if an unseen shepherd is herding them, a hidden giant moving silently in the outer dark. This is the hypothesis of Planet 9, a world several times more massive than Earth, tracing a vast, elliptical path around the Sun. Its proposed orbit is so immense that a single journey around the Sun could take 20,000 years. The evidence is not a direct image, but a gravitational fingerprint, a pattern of orbital anomalies that points to the presence of something large. This potential planet would not be a simple rock or gas ball like the others in our system. It would likely be a super-Earth or a mini-Neptune, a class of planet that is incredibly common around other stars but conspicuously absent from our own cosmic backyard. Its existence would solve one puzzle while creating others. How did it get there? Perhaps it formed much closer to the Sun in the solar system's violent youth and was flung outward by a gravitational slingshot from Jupiter or Saturn. Or, in a more dramatic scenario, our Sun may have stolen it from a passing star system in the densely packed cluster where it was born. The hunt for this world is a monumental task. Astronomers are using some of the most powerful telescopes on Earth, like Subaru and Pan-STARRS, to scan the vast celestial haystack for a single, faint, slow-moving point of light. They are looking for its subtle glow, the tiny amount of sunlight it might reflect from a distance hundreds of times farther than the Earth is from the Sun. So far, it has remained elusive, a phantom at the edge of our maps. Yet the orbital clues are so compelling that the search continues. Finding Planet 9 would be more than just adding a new world to our charts. It would be a profound revelation, forcing us to rewrite the history of our solar system and acknowledge that even our own cosmic neighborhood holds giant secrets in the dark. As we search for hidden worlds within our own system, we must also confront entire galaxies that are fleeing from us at impossible speeds. A star does not simply flee its home galaxy without a story of cosmic violence. Hypervelocity stars are the ultimate runaways of the Milky Way, catapulted into the endless dark of intergalactic space at speeds so great they will never return. Their journey begins with a gravitational catastrophe. The most likely culprit is the supermassive black hole at our galaxy's heart, Sagittarius, a star. When a binary star system, two stars orbiting one another, wanders too close to this gravitational monster, the black hole's immense tide can tear the pair apart. One star is captured into a tight orbit around the abyss, while its companion is flung away at a staggering velocity, a celestial stone from a slingshot on a galactic scale. We have clocked these fugitives traveling at over 2 million miles per hour, a speed that easily surpasses the Milky Way's escape velocity. They are not just fast, they are free. Their trajectories are long, straight lines pointing directly away from the galactic center, a permanent scar of their explosive origin. Identifying them is a painstaking process. Telescopes like Hubble measure the minute shift in the star's light, its Doppler shift, to calculate its radial velocity directly along our line of sight. When that number is impossibly high, a candidate is born. Yet not all these stellar exiles come from the central black hole. Some appear to be flung from the chaotic debris of dwarf galaxies that are being gravitationally shredded and consumed by the Milky Way, their stars sent scattering in all directions. These lone travelers are more than just celestial curiosities. They are probes. By tracing their paths backward, astronomers can map the shape and strength of the galaxy's gravitational field, weighing the invisible dark matter halo that guides their epic escape. Each one is a direct test of the dynamics at the galaxy's chaotic core, offering clues about the behavior of our supermassive black hole. Their ultimate fate is a lonely one, destined to drift through the void between galaxies for billions of years, their light slowly fading as they leave every familiar structure behind. They are living proof of the tremendous forces that can reshape stellar destinies in an instant. This manipulation of gravity and motion on a stellar scale finds its most extreme expression in a phenomenon that warps the very geometry of the cosmos. That cataclysmic merger of black holes does not simply vanish into silence. It sends a tremor through the cosmos, a literal vibration in the geometry of spacetime that propagates outward at the speed of light. These are gravitational waves, the direct consequences of massive objects accelerating through the universe, first predicted by Albert Einstein a century ago. For decades, they remained a theoretical ghost, their signal so infinitesimally small that Einstein himself doubted we could ever detect them. Then, in 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, heard it. The signal was a perfect chirp, a rising frequency that matched the final, frantic orbits and ultimate collision of two black holes over 1 billion light-years away. The detection was monumental, not just because it confirmed a pillar of general relativity, but because it gave us an entirely new sense with which to perceive the cosmos. Until then, astronomy was almost entirely the study of light, from radio waves to gamma rays. Now, we could listen to the universe. The sources of these cosmic ripples are the most violent events imaginable. The inspiral and merger of neutron stars, the collisions of black holes, even the remnant shake from the Big Bang itself. When these incredibly dense objects spiral toward each other, they warp the spacetime around them, and as they accelerate, they radiate energy away in the form of these waves. The information carried within them is pristine. Unlike light, which can be absorbed, scattered, or dimmed by interstellar dust, gravitational waves pass through matter almost completely unaffected. They tell us the masses of the objects that created them, their spins, and their distance, with a clarity that light alone cannot provide. Perhaps the most spectacular demonstration of this new era came in 2017, when LIGO detected the gravitational waves from two neutron stars colliding. For the first time, telescopes around the world and in space were alerted and swiveled to look at the same patch of sky. They saw a brilliant flash of light, a kilonova, the electromagnetic counterpart to the gravitational rumble. The observations confirmed that such cataclysmic mergers are cosmic forges, the factories where the universe creates the heaviest elements like gold, platinum, and uranium. The gold in your jewelry was likely born in the violent death dance of two neutron stars. This coordinated effort, known as multi-messenger astronomy, is like simultaneously hearing a crash and seeing the flash, giving us a complete multi-sensory picture of the event. How do these ripples reveal the dynamics of the universe's most violent events? They are the purest record of gravity in motion, allowing us to witness the final moments of celestial objects as they tear each other apart under their own immense gravity. We are no longer just stargazers, we have become eavesdroppers on the subtle vibrations of spacetime itself. Yet for all our ability to observe the violent present, some of the greatest mysteries are carried by the ancient light of stars that should not logically exist. The Methuselah star shines as a paradox in our cosmic backyard. This ancient sun, officially catalogued as HD 140283, is a ghost from a time before time, a relic whose very existence seems to defy logic. Located just a short cosmic distance away, it is a population 2 star, a classification meaning it is composed almost entirely of the primordial elements hydrogen and helium. It contains only a tiny trace of the heavier metals that fill later generation stars like our own sun. This pure composition is the stellar equivalent of a birth certificate, marking it as one of the very first stars to ignite after the Big Bang, formed from the pristine clouds of the early universe. Its advanced age is written in its slow, fading burn as it transitions into a subgiant. Initial estimates from stellar evolution models placed its birthday at a staggering 16 billion years ago, a number that immediately created a profound cosmological crisis. How could a star be older than the universe itself? Refined observations from the Hubble Space Telescope have since narrowed the estimate to around 14.5 billion years, a figure that, while closer to the universe's 13.8 billion year age, still sits uncomfortably within the margin of error. This tiny but persistent discrepancy is a thorn in the side of our most fundamental models. It forces astronomers to question everything from the precise distance to the star, a key factor in age calculation, to the opacity of the stellar material and the initial amount of helium present in the infant cosmos. Could our understanding of stellar physics be slightly off, causing us to overestimate the lifetimes of these ancient giants? Or does the Methuselah star hold a clue that the universe is subtly older than we think, or that its expansion history is more complex than our standard model allows? This single, faint point of light is a profound reminder that our cosmic clocks are still being calibrated. It challenges the very timeline of existence, suggesting that some of the universe's firstborn suns are still here, quietly watching us from the darkness. If the age of a single star can challenge our cosmic chronology, perhaps the very constants that govern reality are not so constant after all. The laws of physics feel like the one thing we can always rely on, a set of unchanging rules written into the fabric of reality. But what if the rulebook itself is being rewritten? For decades, scientists have operated on the assumption that the fundamental constants of nature are, as the name implies, constant. The fine structure constant, often denoted by the Greek letter alpha, is one of these bedrock numbers. It precisely governs the strength of the electromagnetic force, dictating how light and matter interact, how atoms hold together, and ultimately, why chemistry works the way it does. If this number were even slightly different, the universe would be unrecognizable. Stars might not burn, complex molecules could never form, and life as we know it would be impossible. Yet, a series of audacious astronomical observations have thrown this foundational belief into question. By analyzing the light from incredibly distant quasars, the brilliant hearts of ancient galaxies, astronomers have acted as cosmic detectives. As this light travels for billions of years to reach us, it passes through immense clouds of interstellar gas. These clouds imprint a specific barcode of dark lines on the quasar's spectrum, corresponding to the atomic elements present. The precise positions of these lines depend intimately on the value of the fine structure constant. When scientists measured these ancient barcodes, some teams reported a startling finding. The lines were subtly shifted from their expected positions, suggesting that billions of years ago, in those faraway regions of space, the fine structure constant was minutely smaller than it is today. The change is infinitesimal, a shift of just a few parts in a million, but its implications would be revolutionary. It is a claim that remains hotly debated, with other teams finding no such variation, turning this into one of the most contentious frontiers in modern cosmology. If these findings are confirmed, the ramifications would shake physics to its core. The entire framework of general relativity is built upon the equivalence principle, the idea that the laws of physics are the same everywhere. A varying constant would violate this principle, hinting that something fundamental is missing from our picture. It could point toward the existence of new, unknown forces in the universe, or even suggest that the constants are not fixed properties, but are instead tied to the behavior of hidden extra dimensions, as predicted by string theory. The hunt for a definitive answer is now underway with unprecedented precision. On Earth, teams are using atomic clocks of incredible sensitivity, comparing them over years to see if the tick rate between different types of atoms drifts, which would indicate a change in a fundamental constant. In space, new telescopes are being designed to scrutinize the light of the first stars and galaxies. The central, haunting question remains: are the laws we discover universal and eternal truths, or are they merely local bylaws, a temporary set of conditions in our particular corner of a much stranger and more fluid cosmos? This idea that the very rules of reality might be in flux leads us to confront a structure so immense it seems to break the rules of the universe itself. This giant arc is a crack in the very foundation of modern cosmology. Stretching across more than 3 billion light-years, this colossal crescent of galaxies, gas, and dark matter is not merely big, it is cosmologically forbidden. Its discovery emerged from a patient study of the cosmic backdrop, where astronomers used the light of distant quasars as a probe. As that ancient light traveled for billions of years, it filtered through the sparse gas drifting between galaxies. By mapping the subtle fingerprints of magnesium ions absorbed in that light, researchers could chart the invisible structure of the universe. They were stunned to see a pattern emerge, a coherent, arching wall of matter on a scale that should be impossible. This finding directly challenges the cosmological principle, a cornerstone idea that the universe, when viewed on a sufficiently large scale, should appear smooth and uniform in every direction. The cosmos should not have continents and oceans, it should look like a vast, featureless plain. The giant arc is a continent. Its sheer size defies the standard model of cosmic evolution. From the initial seeds of the Big Bang, there simply has not been enough time for gravity to pull matter into such a concentrated, organized structure over such an immense distance. It is as if you planted a single sapling and returned a year later to find a forest stretching to the horizon. The giant arc is not alone. It has colossal cousins like the Hercules Corona Borealis Great Wall, another structure of bewildering proportions. Together, they force a profound reconsideration of our models. Did the early universe have pre-existing density variations far greater than we thought? Or is our understanding of dark energy and gravity incomplete on the largest scales? This arc is more than a collection of galaxies. It is a question mark written across the sky, forcing us to wonder if the universe's largest structures are still waiting to be found. While we grapple with structures spanning billions of light-years, some of the most dynamic mysteries are unfolding right in our own solar system, on a moon that actively spews its hidden ocean into the void of space. A frozen world in the depths of our solar system is actively spitting its secrets into space. Saturn's moon Enceladus is a small, brilliant sphere of ice, but it is far from a dead ball of rock. At its south pole, colossal geysers erupt through cracks in the frozen crust, shooting plumes of water vapor and ice crystals hundreds of miles into the void. These are not volcanoes of fire, but of ice and water, a process called cryovolcanism. The immense plumes form a hazy halo around the moon, and this ejected material is the very source of one of Saturn's most ethereal features, its broad, faint E-ring. For this to be happening, Enceladus cannot be frozen solid all the way through. The only explanation is a global, liquid water ocean, hidden beneath an icy shell perhaps only 20 miles thick. This subsurface sea is kept from freezing by the relentless gravitational kneading of Saturn. As the moon orbits the giant planet in a slightly elliptical path, Saturn's gravity flexes and stretches its interior, generating friction and heat through a process called tidal heating. This internal warmth is enough to maintain a vast, dark ocean in perpetual liquid state. The discovery transformed our understanding of where life could potentially arise. Our world does not need to orbit in the cozy, warm zone near its star. Life-friendly environments can exist in the cold, dark outer solar system, powered by gravity itself. The true revelation came when NASA Cassini spacecraft did the unthinkable. It flew directly through the towering plumes, sampling their composition as it soared past. The analysis was stunning. The plumes are not just pure water. They contain a rich cocktail of salts, silica nanoparticles, and a variety of organic compounds, the complex carbon-based molecules that are the building blocks of life as we know it. Most tantalizing of all was the detection of molecular hydrogen. On Earth, this molecule is a telltale sign of hydrothermal activity on the deep ocean floor, where superheated water reacts with rock. It is around these deep sea vents, entirely independent of sunlight, that entire ecosystems thrive on chemical energy. The presence of molecular hydrogen strongly suggests that on the floor of Enceladus's dark ocean, hot vents are mixing with the cold water, creating a potentially habitable environment with a ready source of chemical food for any primitive organisms. The chemistry we can measure from afar paints a picture of a world with all the essential ingredients for life: liquid water, a source of energy, and the right chemical building blocks. Could microbes be thriving in that eternal darkness, fueled by the heat of a distant giant's embrace? We do not yet have the answer, but Enceladus has risen to the top of the list of places where we might one day find we are not alone in the universe. This small, active moon proves that habitability can emerge in the most unexpected places, a lesson that shifts our gaze from stars to the worlds they hold. And sometimes the relationship between a star and its planets can turn tragically destructive. A star's final act can be a violent feast. In the slow, inevitable death of a sun-like star, it exhausts the hydrogen fuel in its core and begins to swell, transforming into a colossal red giant. This expanding sphere of hot gas does not politely push its inner planets away. Instead, it engulfs them. A world like our own, with its continents and oceans, would be swallowed whole, spiraling into the star's tenuous but searingly hot outer layers. The planet is vaporized, its substance torn apart atom by atom and churned into the stellar atmosphere. This cosmic cannibalism, known as planetary engulfment, is not just a grim prediction for our distant future. We have seen its chemical fingerprints in the galaxy. Astronomers discover ancient stars with highly unusual compositions, showing a distinct overabundance of elements like lithium, iron, and silicon. These are refractory elements, the very building blocks of rocky planets, which should have been destroyed in the star's core long ago. Their presence is a ghostly signal, the remains of a devoured world now dissolved within its host star. The act of consumption itself can create a brief, observable spectacle. As a giant planet spirals inward, it can transfer gravitational energy to the star, causing a temporary brightening or a detectable surge of stellar activity. This is the ultimate fate that awaits Mercury, Venus, and most likely Earth when our own Sun enters its red giant phase in roughly 5 billion years. Our world will not freeze but be incinerated from the inside out. How many stars in the Milky Way have consumed their own children? Current estimates suggest it could be a surprisingly common end for inner planets, a fundamental process in the life cycle of planetary systems. By studying these stellar signatures, we learn not only about the violent demise of worlds, but also how the material of dead planets enriches the chemistry of the galaxy, seeding future generations of stars and planets with the ashes of the old. This dramatic recycling of cosmic material finds its purest, most ancient form in a different kind of relic, one that has drifted unchanged since the solar system's birth. A foreign object was caught speeding through our solar system in 2017, a dark and silent visitor from the depths of interstellar space. We named it Oumuamua, a Hawaiian word meaning scout or messenger from afar. Its trajectory was unmistakable, a hyperbolic path proving it was not born here. It was our first confirmed guest from another star. Its strangeness became apparent immediately. Unlike most asteroids and comets, it exhibited extreme changes in brightness, suggesting it was tumbling end over end and had a highly elongated, cigar-like shape, perhaps 10 times longer than it was wide. This was unlike any natural object we had ever seen. Then came the most baffling clue. As it hurtled away from the Sun, its speed could not be explained by gravity alone. It was accelerating as if pushed by an unseen force. Comets do this when their ices heat up and vent gas, forming a visible tail. But Oumuamua had no coma, no dusty envelope, no tail whatsoever. It was a dry, rocky-looking object behaving like a comet. This non-gravitational acceleration ignited a firestorm of speculation. Could it be a form of alien technology, a derelict light sail propelled by the pressure of starlight? The suggestion, while highly speculative, was a testament to just how peculiar this object was. The scientific community, of course, sought natural explanations. Perhaps it was a fractal-like aggregate of dust, a cosmic dust bunny so porous and lightweight that solar radiation pressure could push it along. Or maybe it was a shard from a Pluto-like world in another system, a fragment of nitrogen ice blasted away in some ancient collision. Another idea proposed it was a hydrogen iceberg, a chunk of solid molecular hydrogen that would outgas invisibly as it warmed, explaining the acceleration without a visible tail. Each of these theories, however, came with its own set of problems. A nitrogen iceberg would have had to be incredibly large to survive the journey, and a hydrogen iceberg seems too fragile to exist for long in interstellar space. The truth is, we may never know for certain. Our telescopes only had a few weeks to observe it before it faded into the darkness, a fleeting glimpse of a profound mystery. Oumuamua's legacy, however, is secure. It proved that interstellar objects are constantly passing through our solar system, a cosmic traffic we had been blind to. Soon after, we detected a second visitor, the Comet 2I/Borisov, which looked and behaved much more like a typical comet, confirming that Oumuamua was not a singular oddity, but perhaps one of the strangest members of a vast population of interstellar nomads. Each of these travelers is a free sample from another star system, carrying with it the chemical and physical history of its birth. By studying them, we can learn about the building blocks of planets around other suns without ever having to make the epic journey. Oumuamua was a brief, enigmatic postcard from a distant cosmic shore, a reminder that our solar system is not an isolated island, but part of a much larger and more dynamic galactic community. From this single, silent scout, we turn our gaze to an entire galaxy that is in the throes of a spectacular and violent creative explosion. A galactic collision unleashes a firestorm of creation. When two galaxies are drawn together by their mutual gravity, they do not simply pass through one another. Instead, their immense structures plow through each other's spiral arms, sending violent shockwaves through colossal clouds of gas and dust. This cosmic chaos is the primary trigger for a starburst galaxy, a celestial factory where new stars are born at a ferocious, unsustainable rate. The antennae galaxies, a pair of spirals locked in a slow-motion dance of destruction, are a perfect example. Their long tidal tails, stretched out by gravitational forces, look like the antennae of an insect, giving them their name. Within their tangled cores, the compressed gas ignites a frenzy of stellar birth, lighting up hundreds of massive superstar clusters. Another famous starburst, Messier 82, is a galactic powerhouse. Its central region is a maelstrom, churning out new stars 10 times faster than our entire Milky Way. The combined light from all these brilliant, young, hot stars is so intense that it cannot all escape directly. Instead, it is absorbed by the thick cocoons of dust from which the stars were born. This energy heats the dust, causing the entire galaxy to glow fiercely in infrared light, shining not with visible beauty, but with the thermal radiation of its own incredible productivity. This prolific star formation comes at a great cost. The largest stars live fast and die young, exploding as supernova within only a few million years. These continual blasts create powerful galactic winds, fierce outflows of gas that stream out from the galactic core, visible as huge plumes of hydrogen gas shooting out above and below the galaxy's disk. These winds are a self-regulating mechanism. They carry away the very fuel for future star formation, dispersing the gas and enriching intergalactic space with heavy elements forged in the stellar furnaces and supernova blasts. This is how the universe distributes the essential ingredients for planets and life, seeding the cosmic void with the elements of future worlds. The starburst phase is a brilliant, fleeting explosion of activity in a galaxy's long life. It cannot last for more than 100 million years or so, a mere moment in cosmic time, before the galaxy either settles into a quiet middle age or transforms into an elliptical shape, its gas supply spent. This dramatic cycle of collision, fire, and wind shapes the evolution of structure across the cosmos. How many of the serene galaxies we see today were once these raging infernos of creation, and did our own Milky Way experience such violent growing pains in its deep past? These 25 phenomena, from the silent voids to the stellar firestorms, paint a portrait of a cosmos far stranger and more dynamic than we ever dreamed. They reveal a universe built from invisible matter, driven by repulsive energy, and filled with objects that defy our basic logic. Each mystery we solve seems to unlock two more, reminding us that the greatest adventure lies not in the answers we hold, but in the profound, beautiful questions that still beckon from the dark. These threads of cosmic strangeness weave together into a single, breathtaking tapestry. Our journey reveals a universe built not on simplicity, but on a foundation of beautiful, intricate complexity. The quantum connection between particles mirrors the gravitational web that binds galaxies, while the violent death of a star seeds the cosmos with the very elements for life. Each mystery, from the silent dominance of dark energy to the defiant spin of a pulsar, is a fundamental piece of the cosmic puzzle. They are not isolated oddities, but interconnected phenomena that define the origin, evolution, and ultimate fate of everything we see and everything we are. This grand narrative challenges our models at every turn, forcing us to continually expand our horizons and rethink our most basic assumptions. Humanity's quest for knowledge is a journey without a final destination. Every answer we uncover, every paradox we resolve, simply opens the door to a new set of deeper, more profound questions. Our tools grow more powerful, our vision extends further, and with each passing year, we peel back another layer of this infinite cosmic onion. How will the next generation of telescopes and detectors reshape our perspective? The ongoing exploration of space promises to reveal truths more astonishing than any we have yet encountered, perhaps even forcing us to rewrite the rulebook of physics once more. In this strange and beautiful universe, we find ourselves on a fragile world, orbiting an average star in a quiet corner of a vast galaxy. We are the universe become conscious, a way for the cosmos to look back upon itself and ponder its own existence. Our search for meaning among the stars is, in the end, a search for our own place within this magnificent, mysterious whole. The greatest discovery may not be a new particle or a distant world, but a deeper understanding of our connection to the grand, unfolding story of it all. We have traversed a landscape of cosmic wonders, from the invisible scaffolding of dark matter to the explosive fury of magnetars. Each of these 25 phenomena serves as a powerful testament to the universe's boundless capacity for surprise, proving that reality is consistently more bizarre and fascinating than any fiction we could dream up. These cosmic puzzles invite us to remain both curious and humble, standing in awe of the vast unknown that stretches in every direction. The mysteries of space are far more than academic exercises. They are profound sources of inspiration that compel us to look up at the night sky with fresh eyes and a renewed sense of wonder. They drive us to continue pushing the very boundaries of science and exploration, building ever more powerful tools to listen to the ripples in space-time and to peer back toward the dawn of creation. Remember, the universe is overwhelmingly vast, and our own understanding is still in its infancy. If this journey through the strange and beautiful cosmos has sparked your imagination, consider subscribing for more deep dives into the wonders of space. We would love to hear which phenomenon amazed you the most, so share your thoughts in the comments below. Keep looking up, for the greatest discoveries are undoubtedly yet